If this deposit is significant and everything we've measured says it is, why is it still just sitting here? What you're looking at is over 6,000 individual radiometric measurements, taken on foot across a steeply dipping mineralized vein system in the Powderhorn district of Gunnison County, Colorado. The hottest readings correlate directly with a 1956 USGS survey that identified this zone as one of the highest grade thorium occurrences documented in the district. And yet, the ore is still in the ground. The geology hasn't changed. What changed decades ago was the political and institutional calculus around what thorium was actually worth, a decision that most people were never exposed to.
The President of the United States said,
"This plant has a secure place in American history."
Two elements, thorium-232 and uranium-238, and its scarce cousin, uranium-235, radioactive, heavy, and capable of releasing enormous amounts of energy. But they behave very differently, and that difference is everything. Thorium is 3 to 4 times more abundant in the Earth's crust than uranium, but natural uranium ore contains two isotopes in very different proportions, U-238 at 99.3% and U-235 at just 0.7%. Only U-235 can directly sustain a chain reaction. The enrichment process runs on a single scale: low-end, reactor fuel; high-end, weapons-grade material. Same process, same infrastructure, just taken further. Thorium's conversion product is contaminated with a powerful gamma emitter that makes weaponization difficult. The dual-use pathway that made uranium so strategically valuable to the weapons program is far less accessible with thorium. Uranium-235 is fissile. Strike a match, it catches. It splits directly and sustains a chain reaction. Thorium-232 is fertile, wet wood. It needs conversion before it becomes useful fuel. But once it's ready, it burns just as well. Unlike uranium, essentially all the thorium you pull from the ground is the isotope you want. The conversion is designed to happen inside the reactor as it runs. Here's how that conversion actually works. A reactor supplies a free neutron. Thorium-232 absorbs it, becomes unstable, and decays twice through thorium-233 and protactinium-233, emerging 27 days later as uranium-233, fully fissile. A breeder reactor, one that produces more fissile fuel than it consumes, converts that wet wood into dry wood. There's one more difference worth understanding: what these fuel cycles leave behind. Uranium cycle waste contains isotopes that remain hazardous for 10,000 years or more, depending on reactor burnup and fuel composition. For instance, plutonium-239, one byproduct of conventional uranium reactors, has a half-life of over 24,000 years. This is a simplified comparison, but the difference is in the long tail. Thorium cycles reduce the long-lived fraction of the waste, changing the timescale of the problem. These differences were understood by the scientists involved. They simply weren't the deciding factor. August 1945. The war is over. The United States has just demonstrated something the world had never seen: energy released from the nucleus of an atom at a scale that ended a war in 2 flashes of light. The question now was what to do with it. In the years that followed, 2 serious nuclear paths were actively researched. One used uranium and plutonium, the fuels that had just ended the war. The other was built around thorium, more abundant, with a cleaner waste profile, and with no straightforward path to a weapon. For a brief window in the late 1940s, the choice between them was genuinely open. What closed that window was gradual. Institutional priorities accumulating over a decade, until one path had everything behind it and the other had very little.
Today, whatever you are, whatever you do, wherever you may go, you are a part of atomic warfare. It involves you, personally.
Admiral Rickover changed everything. In 1953, Rickover drew a sharp line between what he called paper reactors, theoretical designs that looked good on paper, and practical reactors that could actually be built and deployed. The pressurized water reactor was practical. The molten salt reactor was not. Not yet. Assigned to the Navy's nuclear program in 1946, Rickover became the driving force behind a pressurized water reactor design. Compact, powerful, and built for endurance. His goal wasn't civilian power. It was a submarine that could stay submerged indefinitely, cross the Arctic, and carry weapons that could reach any city on Earth. In 1948, the AEC contracted Westinghouse to build that reactor. 7 years later, Commander Eugene Wilkinson transmitted 4 words: "Underway on nuclear power."
Military units work continuously with the laboratories of the Atomic Energy Commission and their new weapon ideas.
Private capital started flowing. Westinghouse and General Electric built out entire industrial divisions around the pressurized water design. Thorium did not develop the same institutional momentum, not because the science was weaker, but because thorium couldn't produce what Rickover needed, alongside a broader set of Cold War priorities that reinforced that path. It wasn't suited to fueling a submarine in the way the Navy needed, and it didn't integrate cleanly into the weapons-grade plutonium production pathway that uranium did. In the Cold War calculus, those weren't minor shortcomings. The same enrichment infrastructure that produced reactor fuel produced the material for nuclear weapons. The same institutions that built civilian power plants built the arsenals. Uranium served both masters simultaneously. Thorium served neither. Alvin Weinberg ran Oak Ridge National Laboratory for nearly 2 decades. He briefed senators and presidents. He was not a fringe figure. He was present at the creation of American nuclear science. And he believed, genuinely, stubbornly, to the end of his career, that the molten salt reactor was the right path. In 1965, his team brought the molten salt reactor experiment to criticality at Oak Ridge. It ran for 4 years. By 1967, the molten salt reactor had logged 6,000 full power hours. Weinberg was celebrating. He had every reason to. But inside the Atomic Energy Commission, the argument for thorium was becoming harder to make, not because the science had failed, but because the institutional priorities had long since moved elsewhere. In 1973, Weinberg was removed from his position at Oak Ridge. Partly, his colleagues said, for pushing the thorium path too hard. The MSRE program was defunded. The equipment was mothballed. Years of quarterly progress reports, a reactor that worked, and then silence. So let's come back to the ground. The deposit we've been documenting, Little Johnnie, in the Powderhorn district of Gunnison County, is a mineralized fault zone hosted in Precambrian metamorphic rock. The grade is extraordinary. But grade alone doesn't make a mine. The mineralized zone is narrow, somewhere between 2 and 6 feet wide. It dips steeply, close to vertical, and its continuity at depth is unknown. Nobody has drilled it. A deposit like this would require underground narrow vein mining methods, expensive, technically demanding, and difficult to justify without significantly more exploration data. A few miles to the south sits Iron Hill, a carbonatite alkalic complex, genetically related to the same magmatic system that produced this deposit, but very different in character. Where this deposit has grade, Iron Hill has scale. A 1979 USGS resource assessment estimated Iron Hill's measured reserves alone contain roughly 13 times the thorium of this vein, and that's before accounting for the additional probable resources at depth. Iron Hill also contains significant rare earth elements, making it a far more complex economic proposition. But for our purposes, the thorium alone is distributed across hundreds of millions of tons of lower grade rock, requiring massive open pit extraction and complex metallurgical processing. This deposit has the grade, but not the geometry. Iron Hill has the tonnage, but not the grade. Under any realistic economic framework, before you even get to politics, neither deposit offered an obvious path to production. The Powderhorn district ranks 4th among the major national thorium vein districts by any measure of scale. Lemhi Pass on the Idaho-Montana border holds nearly 40 times the reserves. The Wet Mountains district, right here in Colorado, holds 30 times more. But here's what that context actually proves. These were the high-grade vein deposits, the ones considered most economically viable to mine, precisely because of their concentration, not bulk low-grade carbonatites requiring massive open pit operations. The deposits that made the most economic sense on paper, and even those failed to reach commercial development. The scale of institutional abandonment goes further still. The US government had accumulated over 3,000 metric tons of thorium nitrate in its national defense stockpile, a byproduct of rare earth processing, not from deposits like these. Rather than develop it, they classified it as low-level radioactive waste and buried it in Nevada. Not a safety emergency, largely a cost accounting decision. The resource was there, the institutional will was not. Even if this deposit were 10 times larger, it would have stayed in the ground, because the deposits that were 10 times larger stayed in the ground too. And the stockpiles that were already refined and ready to use got buried. What this ground represents, what every thorium deposit surveyed and quietly set aside in the post-war decades represents, is a decision made in Washington that the people who surveyed this hillside probably never fully understood they were subject to. The survey happened because thorium was briefly valuable. The abandonment happened because the Cold War redefined what valuable meant. And this deposit has been sitting here ever since. The Chinese Academy of Sciences didn't arrive at this empty-handed. When they launched their thorium molten salt reactor program in 2011, they built directly on what Weinberg's team had proved. The knowledge was there for the taking. They simply had the institutional will to pick it up. In June 2024, their reactor, the TMSR LF1, reached full operational capacity. And in November 2025, they announced something that would have made Alvin Weinberg stop in his tracks. For the first time, thorium-232 had been successfully converted to fissile uranium-233 inside a working reactor. A demonstration, not yet a power plant, but proof that the physics still holds. The molten salt path Weinberg proved in 1969, the one that got his program defunded and eventually cost him his position, China just proved it again. It isn't just China. In the Netherlands, the Horizon is targeting Europe's first commercial MSR by 2034. In Denmark, Copenhagen Atomics is building a thorium reactor designed to fit inside a shipping container. India's three-stage program is advancing toward a thorium fuel cycle. The road not taken is now being walked by people who inherited Weinberg's knowledge and are still navigating the same institutional, economic, and regulatory resistance that buried it the first time. This hillside hasn't changed. What has changed is everything around it. The world those decisions were made for looks very different now. And that conversation is being taken seriously again by people with real money and real programs behind them. Just not here. Not yet. The ore is still here. The physics still work. The decision that left this ground untouched was made 70 years ago by institutions responding to pressures that have since changed shape. Whether anyone is paying attention is a different question.